So now we've seen that the fundamental quandle for a knot is an algebraic structure whose structure was specifically built so as to be a knot invariant, in other words, specifically built in a way that makes it invariant under the Reidemeister moves and therefore a property of knots and not a property of diagrams. And we've also at least persuaded ourselves why the fundamental quandle of a knot should encode so much information about that knot that it can be a complete invariant for knots. So the last thing that we want to do is explore a little bit about how other kinds of knot invariants can be distilled out of the fundamental quandle to give us kind of a shadow or a viewpoint on the fundamental quandle, if you will, that can give us really powerful knot invariants, even though they don't necessarily tell us everything about the fundamental quandle, which in general is a really, really complicated and too large of an object to wrap our heads around. So we're going to look at some examples of invariants that we can get out of the fundamental quandle, and our first example will be the knot group. So remember, the way that the fundamental quandle worked is that its elements were generated by all the arcs in a knot diagram, and moreover, we imposed all of the relations that would be imposed upon the arcs in this diagram by the requirement that every arc, which is the outbound undercrossing of a crossing, is related to the other two arcs that it's crossing by the crossing operator. And we impose all of the relations that make the crossing operator a quandle operation. So the fundamental quandle has all the information we could ever hope to have about a knot encoded in one single type of algebraic structure. But a quandle is a different kind of algebraic structure than we typically study in undergraduate abstract algebra, for example. And in abstract algebra, we tend to study groups that are a little bit simpler, groups that have operations that are binary, which are associative, which quandle operations are not, which are invertible, which quandle operations are, and which have identity elements, which quandle operations kind of do, except insofar as every element is an identity element in a sense, right? Because everything crossed with itself gives you itself. So quandles are a bit different than groups, but it turns out that the two are intimately related in a particular way that gives us a knot invariant, which is itself a group. It's called the knot group of a knot. So to define the knot group of a knot, we say in topology that the knot group is the fundamental group of the knot's complement inside of the three-dimensional sphere. In other words, what this means is if the knot is sitting inside of space, we drill out the knot out of space and consider all the space that's around the knot and not the knot itself. So essentially what we're doing is we're looking at the three-dimensional object which includes everything in the universe except for the knot itself. And the fundamental group is giving us what we call homotopy classes of loops that go around, that originate from a single base point in that three-dimensional space. So the elements in this group are loops, or homotopy classes of loops, sitting inside of three-dimensional space. As long as those loops do not intersect with the knot itself, they will be loops in the knot complement. So how do we get the knot group out of the fundamental quandle? Well, formally speaking, we can say that there is a functor from the category of finitely presented quandles to the category of finitely presented groups. And what it does is it realizes the quandle operation as conjugation of group elements. In other words, the purpose of this functor is to create an algebraic structure where the objects in my structure are the same as the objects were in my fundamental quandle. In other words, to every arc of my knot diagram, I'm going to associate a generator of this group. And in place of the quandle operation, what I have is a conjugation operation, which is a familiar thing if you study group theory, but it's now sort of elevated to this importance when we study knots. What we're going to get out of this is a presentation for what's called the knot group, the fundamental group with a knot complement. And that presentation is going to specify the generators, and we're going to have one generator for each one of the arcs in our knot diagram, and it's going to specify a bunch of relations. As you might expect, there's going to be one of these types of relations for every actual crossing in our knot diagram. So, what does this actually look like? First of all in theory, and then second of all in practice. So suppose that I have a knot diagram with a crossing in it like this, and I've sketched this in such a way that this crossing is a positive crossing. So as we go underneath the bridge in our car, the traffic on the bridge is moving from our left to our right. So the way that the knot group works is that we're going to be able to associate with every arc in our knot diagram a generator. And that generator, in the fundamental group of the knot complement, those generators, those elements, are going to be just loops, little loops that go just around the arc that it's associated with. So if my overcrossing arc right here, if I call that arc y, then I can associate with that arc this little loop that goes around, just around that arc. It doesn't loop through any other arcs, and it only goes around once, but that gives me one element in my knot group. And so up to homotopy, in other words. Homotopy means that we can move and slide these loops around in any continuous fashion that we want to, as long as they don't leave the knot complement. And what that means is as long as they don't intersect the knot when we try to slide them around. So this green loop over here on this side of the y arc is the same up to homotopy as this one over here. Technically, we should be specifying a base point for all of these, which I'm going to do in just a second. But just for convenience for drawing the diagram, I'm going to draw it as though it's just a free homotopy. So we can slide this loop around to here, and this little green loop is going to represent y. We'll also use the convention, that's the right-hand rule. In other words, if you point your thumb in the direction that the arc is oriented, then your fingers are going to curl in the direction that that generating loop actually goes. So those are what the elements look like, and at every crossing I'm going to have an x, a y, and a z as three distinct elements of my knot group. So what happens when I multiply in this knot group? What does the operation in the fundamental group actually look like? Well, what we can think of as x times y is actually called concatenation of these two loops. What it means is we're going to go around the x strand, and then we're going to take a trip around the y strand. And when I fix a base point up here that's sort of sitting above all the strands in my crossing, what xy is going to look like is it's going to start from the base point, it's going to make a loop around and underneath the x strand, then it's going to loop underneath the y strand, and it's going to go back up to the base point. So that's the big loop in the knot group, which is called xy. So at this crossing, xy is going to be some loop that crosses underneath two of my strands over on this side of the crossing. If I then take this loop and I pass it underneath the crossing to the other side, now this is going to be expressible not in terms of x and y, but in terms of y and z. And in particular, so this purple loop that I get from starting at the base point up here, looping first underneath the y strand, and then underneath the z strand, and then back to base, that loop is going to be called yz. But since loops in the knot group are only defined up to homotopy, in other words, I can move and slide them around in any continuous fashion as long as I don't try to slice them through the knot itself, we can see that the orange loop, xy, and the purple loop, yz, are homotopic one to another. They're homotopy equivalent because all we did to get the purple one was just slide the orange one underneath the crossing and bring it over here. So those two are homotopic, and therefore in the knot group they are equal. So xy is equal to yz in the fundamental group of the knot complement. So what that's doing is it's defining for me how to get z in the knot group out of x and y. It is obtained by a relation that looks like this. And also, in the fundamental quandle, because z is the outbound undercrossing arc and x is the inbound undercrossing and y is the overcrossing, we also know that in the fundamental quandle, z is equal to x cross y. So what this functor is doing is it's setting up this correspondence, that every z arc, which I get by doing x cross y in the fundamental quandle, corresponds in the knot group to a z element, this little blue loop, which is homotopic to the result of y inverse, so go once around this backwards, followed by x, followed by y. It's just by solving this equation over here for z. And we can check that this conjugation operation satisfies all of the properties that we need a quandle operation to satisfy as well. And so all of the structure that exists in the fundamental quandle, most of the structure anyway, that exists in the fundamental quandle, is going to be replicated over here in this knot group. So conjugation is a quandle operation, and therefore the knot group that we get out of this gives us a whole lot of information about the knot. So what a knot group looks like according to this is it's a free group that's generated by the arcs in my knot diagram, x, y, z, and so forth, if I have a bunch more arcs. And the relations in my presentation are just these conjugation relations. Every time I have arcs x, y, and z meeting at a crossing, I will get a relation of the form z equals y inverse xy. So this tells me everything that I could need to know about the fundamental group of the complement of a knot, called the knot group, in what's called the Vertinger presentation. The Vertinger presentation is just a presentation of a group where all of the relations in that presentation are defined by conjugations. So that's great. And the knot group, because it's distilled out of the fundamental quandle in this way, is a knot invariant. It's a pretty powerful knot invariant, but it's not actually all powerful. We can find, for example, distinct knots that do have the same knot group. Even though their fundamental quandles will be different, we lose a little bit of something in this functor. We forget a little bit of structure when we go from quandles to groups. Just enough that the knot group doesn't have as much power to distinguish knots as the fundamental quandle does. Also, the fact that the best that we get out of this is a presentation. Presentations of groups are notoriously challenging to work with. Knot groups also are always going to be infinite groups. It's never going to be a finite group because, for example, if I take one loop around this X strand, that gives me one element, but I could loop around it twice and get a distinct element. I could loop around it 3 times and get a different element, and so forth. So every one of these elements is going to have infinite order in and of itself. So these are always infinite groups, and the structures can get fairly complicated if we have a whole lot of different crossing relations. But at least we know that this is a recipe that can define for us the knot group for a knot. Okay, so what are some other invariants? Besides knot groups, what else can we get out of the fundamental quandle? Let's talk some more about that Alexander module that we saw in the previous video. What we'd like to do is be able to wrap our minds around it a little bit more. Remember, the Alexander module is what we get by looking at the magic averages evaluated on every arc of a knot diagram, where I can assign now Laurent polynomials in T with integer coefficients to any of my arcs, evaluate the magic average, which is this expression, and that's going to give me a set of values which are also Laurent polynomials in T. And the Alexander module is the result of taking the domain of this linear transformation and taking the quotient by the kernel of this linear transformation, where the kernel is the space of all valid colorations of my knot. So all of those in which all the magic averages at every crossing are equal to 0. So lambda to the n quotiented out by the kernel of this transformation gives me the Alexander module. But that too, even though it's a knot invariant, is challengingly large to understand. So what we're going to do is we're going to try to slice it up a little bit, one so-called elementary ideal at a time. So we know, for example, that if I build a matrix for this linear transformation, then the row space of that matrix is going to be one way of understanding this Alexander module. We also happen to know that this matrix is always going to have a determinant of 0. Why? Because this matrix is never an invertible matrix. Even when it's a square matrix, it's never going to be invertible because there always exists a non-trivial element in the kernel of this transformation. Specifically, because every knot diagram is one colorable, we can always write down a trivial coloring, which is going to be a multiple of the color vector 1, 1, 1, 1, 1, 1. And because that will always give us a valid coloration, this transformation will always send those elements to 0. So the kernel is always non-trivial, therefore the determinant of this entire matrix is always equal to 0. To look at an example, let's go back to the trefoil, for which we can write down this, what we call presentation matrix for the Alexander module. This is the matrix of which the row space is equal to the Alexander module itself. And when we do the row reduction on this, as we did at the beginning of our last video, we can find that a basis for this row space consists of the first 2 rows. And I mentioned at the time that this element right here that's on the diagonal, which is part of our second row, this element is special somehow. Right now, what we're going to do is we're going to call that element the Alexander polynomial of this knot. Now, formally, what is the Alexander polynomial? Well, what happens when I row reduce a matrix enough to get it into its row echelon form, so I only have zeros below the diagonal, is this element, because I also happen to have a 1 up here in the upper left-hand corner, this element is actually the same thing as the determinant of this 2 by 2, what we call a minor, 2 by 2 minor of this matrix. Its determinant is 1 minus t plus t squared. And it turns out, and this was a result that was proven, again, early 20th century, it turns out that for these matrices, the determinant of any 2 by 2 minor is going to be a multiple of the same polynomial. So any 2 by 2 minor of this matrix that I pick, even if it's not the upper left-hand one, if I cross out any row and any column of A, and I take its determinant, what I'm going to get is a multiple of this 1 minus t plus t squared. So we call the first elementary ideal of this module, we call that the ideal that's generated by the n minus 1 by n minus 1 minors of this matrix. And that ideal is always principal, which is what I was saying a second ago. Every element is a multiple of one single generator. And that generator up to a normalization constant is called the Alexander polynomial. And the normalization factor that we insist upon is that we want it to be a polynomial, so we want none of the exponents to be negative, and we also want the constant term to be a positive number. So as soon as we insist upon those, that actually uniquely defines the polynomial which generates this first principal or first elementary ideal, and we call that polynomial the Alexander polynomial of this knot. It's a knot invariant because we discovered it through an algorithmic process applied to the Alexander module, which itself is a knot invariant. So this is really cool. It now associates a polynomial to every single knot. All I have to know is I have to know how to write down the presentation matrix for its Alexander module, and then all I have to do is take the determinant of any of its n-1 by n-1 minors. And once I normalize it so that all of its exponents and its constant term is positive, then I get the Alexander polynomial, and then that's uniquely defined. So Alexander polynomials are really cool, and you can do a lot with them. Unfortunately, like the knot group, they're not all-powerful either. When I apply the process to these two nasty 11-crossing knots, which we've so far been unable to distinguish with our knot invariants, it turns out that these two 11-crossing knots have the same Alexander polynomial. So even the Alexander polynomial is not enough to distinguish these two knots one from another. So that's kind of disappointing. And so at this point, we've gotten to such a sophisticated invariant, and we haven't found a disagreement. Maybe these two knots actually are the same, after all. Well, the good thing is we can repeat this process to dissect the Alexander module a little bit further. And instead of looking at the n-1 dimensional minors, what about the n-2 dimensional minors? As we take smaller and smaller subdeterminants of our Alexander module presentation matrix, we get more and more different ideals that are each associated with our Alexander module in an invariant way. So all of these ideals are themselves not invariants as well. If I take the n-2 by n-2 minors, those generate an ideal which is no longer a principal ideal. So I can't get away anymore with just taking one of them and being done. I need to be able to understand the ideal which is generated by all of the n-2 by n-2 minors. But when I do that process for these two knots, for the knot on the left, the ideal generated by its n-2 minors is actually the entirety of the ring lambda of Laurent polynomials in T. But for the knot on the right, the n-2 by n-2 minors generate an ideal which is not actually principal. It's generated by the polynomial 3 and the polynomial 1 plus t. And so, in other words, this second elementary ideal for this knot is strictly smaller than the second elementary ideal for this knot. And therefore, because all of those elementary ideals are not invariants, we now know that these two knots cannot be the same knot. So we had to go pretty far before we found an invariant with sufficient power to distinguish between these two knots, which was also something that was computable. If we believe the fundamental quandle distinguishes all knots up to chirality, then the fundamental quandle will certainly distinguish these two knots one from another. But because that's such a hard thing to compute, knot theorists are almost always left with the option of distinguishing between knots by computing simpler invariants. And in this case, the Alexander module is enough to distinguish between these two, and the way that we know that is because the second elementary ideals disagree. So if the fundamental quandle is all-powerful, why doesn't it completely close the book on knot theory? Well, again, the fundamental quandle is impossible in general to compute. We can't expect that we can just write down the fundamental quandle for knots to distinguish between them. But fortunately for us, there's still a lot of open questions out there that lesser knot invariants, like the Alexander polynomial, like all of the other polynomial invariants and algebraic invariants which are associated with knots, and there are dozens in the field. There's still a lot of very active work that's going into resolving questions of differences between knots using those not quite complete but still very powerful other invariants, which in principle we can discover from the fundamental quandle, but which are much more tractable to understand than the fundamental quandle itself. And so that's it. If you're interested in more information about anything that was in this seminar, a couple of great references that have inspired me a lot in this semester have been Colin Adams' book, The Knot Book, which you can find. It's published by the AMS. and more recently, the book by Mohammed El-Hamdani and Sam Nelson called Quandles, An Introduction to the Algebra of Knots. It's a terrific read, and it approaches everything about knot theory from this algebraic perspective. So it builds all the way up to the fundamental quandle, and then also talks about some of the more recent questions that are being asked about quandles and associated structures that have been assigned to quandles and generalizations of quandles and so forth. So it really is a pretty deep dive, but it's a very accessible read, and both of these books are really accessible reads. So both of these are great. You can also, again, check out my site, mathematics.com/OAK, for more resources from our knots theory and algebra graduate course this semester, including this video and also associated resources. So I hope you enjoyed, and happy knotting.